And I'm asking Linda to throw up the PowerPoint when she gets to it. But I'm going to start talking. And I'm going to advance the slide once. As always, I'm going to talk for a while. I'll give Linda an opportunity to talk, say whatever she might want to say. And certainly student questions and answers are always welcome. And you can say those any times, but there's a time slot there for that. But tonight, what we're going to do is we're going to, well, look back just a little bit, but not a lot. For the most part, we're going to move on and talk about projectile motion equations and do some projectile motion problems. So that is the plan for tonight. I guess the first thing I'll say is that I am pleased that we're on schedule and on track to cover everything that we want to do, and that's the reason we're continuing to move forward with the physics. My first bullet point here says accommodations are moving along. They're moving along, but they're moving along kind of sluggishly. I have not been able to find any responses to the forms that I have submitted. And so tomorrow I'm going to go and stand in front of someone's office and unravel this mystery of where those forms went when I set them where I was supposed to send them. So that will be happening. So I expect to be able to give you something more definitive later. But please understand, I plan not to rest until all the accommodations are rendered. And so that probably means I have miles to go before I sleep, but I'm prepared to do that. Okay, I did send you recently, and I don't know if it was yesterday or this morning. I think it was yesterday actually. Several more videos for you to watch. Moving us through this projectile motion kinds of things, and also clarifying and posting LSA that are in physics, and I'll call these LSA P0, P1, and P2. And what I'm going to be doing also is I think I'm not going to wait for all the accommodations to happen. I'm just going to grade things. And for those of you who did not require accommodations, at least you'll have feedback. So that's what I'm planning to do. Begin tomorrow as well. I was hoping to have all the accommodations done, but that certainly didn't happen. Also, please be on the alert that there's LSA, which I call physics, the third one, but that's really the fourth one because we have 0, 1, 2, and now 3 will be available in the material tonight. The net group test is to be finished tonight, so I hope to be able again to provide the students who have not been accommodated or who did not require accommodations, sort of a year-to-date status, so you'll know where you are, and that's good. So that's kind of my theme there. And if you think that the accommodations are kind of a sore point with me, not that it's students deserve accommodations and things like that, but that's been so awkward doing them. You're right. That's a little bit of a sore point with me. But I hope to make major progress tomorrow in between teaching my classes. Okay, that's all I really want to say there. Linda, do you have anything that you would like to share with the group?
Nothing too exciting. Nobody showed at the guided study group tonight, so just so you guys know, that is still an option going forward with the physics topics. If you guys don't like this time and it's really just not working for you, then please let me know as well, and I can see about rescheduling it if it's really an issue with people's schedule.
And I really think that if you go and look at this P0, P1, and P2, and this is just me talking, and P3, I don't think that these are easier than the statistics problems. In fact, in my way of thinking, they might be more difficult. And so I would encourage you to take advantage of the support that Linda's providing. And also, I would encourage you to, you certainly can come to my office hours. And there have been some students who started coming to my office hours a little bit. And in fact, I worked in special session with, one of your classmates over this weekend. And I actually think it was a good session. I think the student benefited from, being face-to-face instead of remote. And the situation was so, it was safe for them to do that. Because the Learning Commons takes a lot of care with those things. Okay, so Linda, if there's nothing else, I'm going to move on to the student Q&A. And so I'm just throwing this open. I'll count to 10. Mississippi, again, your comments are always welcome. And so you don't have to make them now, but this is a good time for you to make them perhaps. So I'm beginning my count now. Okay, no one has anything they want to raise at this time, which is fine. So we're going to move into content. Okay. Now, the first thing I'm going to do is we are going to look back just a little bit. We're basically in chapter 3 with the videos that I have posted. And so again, we're on track, but we're going to be doing things tonight. And I want to recall a couple of equations here. And these are actually from chapter 2. But they're important for you to know. And one of them is that, and you should realize that velocity and acceleration are both vector quantities. And so they have magnitude and direction. But the average velocity is the change in location. This is x2 minus x1. Those are locations divided by t1, t2 minus t1. And we call that delta x over delta t. And that's the average velocity. But then the acceleration is the change in velocity divided by the change in time. So that is v sub 2 in the x direction minus v sub 1 in the x direction divided by t2 minus t1. And so that's a vector quantity. So both of those have magnitude and direction. Now, if we're talking about rectilinear motion, this is what we're talking about in chapter 2, we're talking about things that go either straight up and down or straight horizontally. But now there are equations that come from these. And these, again, are the big equations that you learned in chapter 2. And that's it, that and sometimes this is called final velocity. Here it's called velocity at time x is equal to the initial velocity plus the acceleration times the time. So that's an important equation that you want to be familiar with. Another equation that comes from this is if you want to know where you are now, it's where you started plus the velocity initial times the time plus, and this is 1/2 acceleration times the time squared. Okay, and then last but not least, but very importantly, this last equation is very useful whenever you're not given time. Notice that the two equations that we just talked about have time in them. This does not have time in them. Time has been eliminated from this. So we have v sub f, v sub final, or v sub at a certain time x squared is equal to v initial squared plus 2ax, a in the x direction, times delta x, x minus x0. So you see, these are important equations that you will be using, and so you want to gain some familiarity with using these. Now let's move to our first genuine example of tonight, and that's going to be this problem 62. And Linda, I think what I would like to do is after I read this, I would like to ask the students to work on this for a while, and they can be using those equations that we just talked about in order to deal with these. But then we'll talk through this, and we'll also do this with 63 as well. I realize this is looking back, But what we're going to be doing tonight with projectile motion is even more complicated because we're having motion that's in a plane. There are some X directions and there's some Y directions that are both combined. So I'm reading number 62 for everyone in the class. And Linda, if I can ask you to be prepared to kind of, count 5 minutes or so for students to work on this, and then we'll come back and do a solution. I don't think breaking the student into groups works very well, but that's what I think we'll try to do. Okay, so I'm reading it first, and then we'll do this. At the instant the traffic light turns green, an automobile that has been waiting at an intersection starts ahead with a constant acceleration of 2.50 meters per square second. Now, at the same instant, a truck traveling with a constant speed of 15 meters per second overtakes and passes the automobile. Now, this means that this truck driver had no intention of stopping at all. They were tooling along, but he, I guess, was guessing that the light was going to change, and so he just continued moving at his constant speed, which is 15.0 meters per second. He overtakes and passes the automobile because the automobile was just sitting there. He was moving, and so he passes it. Now, what eventually will happen, since he's going at a constant speed, the automobile will one time catch up. And in fact, I guess that's what we're asking. So how far beyond its starting point does the automobile overtake the truck? So that is part A. And then part B is how fast is the automobile traveling when it overtakes the truck? So Linda, if you will kind of start your count and let me know when 5 minutes has elapsed, and then we'll go through and we'll discuss a solution to this.
Okay, it's been 5 minutes.
Okay, thank you, Linda. And again, 5 minutes is about half the time on average that you have to solve this problem. But this is valuable doing this because it allows you to try to come to grips with the equations and perhaps prepare yourself to understand the solution. So let's look at this number 62 then. Okay, now here's some thoughts and we'll talk through this. So and I think I can try to use my pointy thing and maybe you can see my pointy finger now. Linda, can you see my pointy finger?
I cannot.
You cannot. Okay, maybe that means that doesn't work the way I was hoping it did. So what I'm going to do is I'm going to take the pencil. I might not write much, but at least you maybe can see the pencil. Okay, so here's what we're going to be doing. And we're going to be looking at, and I need to, that's in the way now. Okay, so what we need to do is we need to say, all right, the car is going to overtake the truck when they've traveled the same distance. Okay, so they both traveled a distance d. Okay, so let's first of all talk about the car. Well, the car was starting at rest, so its initial velocity was 0. And it had a constant acceleration, and the acceleration was 2.5, that's meters per second squared. So now we have a formula for that, and this is the formula. The change in distance is going to be the initial velocity times the time plus 1/2 the acceleration times t squared. So the distance for the car, though, since the initial velocity was 0, it was at rest. There's no contribution from this first part, and it's just 1/2 a in the x direction times t squared. So this is going to be, this is the distance of the automobile. It is going to be 1/2. This is 2.50 meters per second squared times, and we're going to call it capital T because we're letting that to be the time that the car overtakes the truck that just plowed through the stop sign. Okay, so that is 1/2 2.5 times t squared. Now the truck is different. The truck has an initial velocity at the stoplight of 15 meters per second. He did not stop. He was going just at a constant velocity. But the acceleration was 0 because the velocity was constant. There was no change in velocity. So D is equal to, I'm using the same equation that I have up here, but the change in distance is going to be v0, his initial velocity times time, plus 1/2 the acceleration times t squared, but the acceleration this time is 0. So d in this case is 15 times 15 meters per second times the time. So we're going to set these two things equal to one another. And so that means we have 1.5 meters per second squared times t squared equal 15 meters per second times t. And we have to solve this and get t equal to 12. Now let's talk about what the solution of this actually looks like. And Linda, I'm going to try to write this down here and let me know if this isn't showing up well enough or something like that. So we say this is 12.5 t squared is equal to 15 times t. But I'm going to subtract that, and this is going to be 15t. And that's going to be equal to 0. Now, this, and the reason I'm going through this, I want you to understand where the 12 comes from. There really are two solutions. And we're saying T was when the truck and the car were next to each other. Well, one was the instant the light changed when the truck passed.
I think that should be a 1.25, not a 12.5.
Thank you, and I'll fix that. And let's see, I have to think about how I can erase that. I'm trying, that seemed to work. Thank you, Linda. Okay, so that's what's happening. So now I'm going to factor. Linda, I was so excited about doing factoring here that I was just dropping ahead with that. Okay, so this is going to be 1.25 times t, and then this is minus 15 is equal to 0. Now what we have is two things being multiplied together equaling 15. So one of these two things has to be equal to 0. So either the first factor, which I underlined first, could be equal to 0, which is true. When they were right at the stop light before it changed, the instant before it's changed, they were both right together. But once it changed, then the truck raced ahead. So anyway, from this we get a solution that we really don't care about because the problem didn't, we knew that they were together there. But that will give you t equals 0. But this is the one that's more interesting. So this is 1.25, and this is t, minus 15 is equal to 0. So what we will do is add 15 to both sides. This is algebra, and we'll divide by 1.25, and Linda will do that for us just to confirm. But we get that t is 12 seconds. Okay, questions on that? Yes, Monica.
I'm sorry, can you repeat where the 1.25 came from again?
Yes, I can. 1.25 is the is 1/2 times, and so I'm going up here. I'm drawing this again, but is 1/2 times 2.50. So that is 1.25 times t squared. So I think I answered that one, Monica.
Okay,
All right,
thank you.
so t equals 12 seconds. But then the problem asks, so how far down the road did the car catch up with the truck? Well, you see it was 12 seconds before it caught up. So you could say, well, how far did the truck go? Well, distance equals rate times time. So the truck went 15 times 12 is 180 meters down the road. So that's the answer to part A. Now I don't remember, so I'm going to go back and check it out. I don't remember what the second question was. Oh, B said, how fast is the automobile traveling when it overtakes the truck? So that's a good question, and that's another question that happens. Okay, so what we're going to say is that and I think I need to get a hold of the drawing tool again. Okay, so again, we're going to use the equation that the velocity, the final velocity, is equal to the initial velocity in the x direction times the acceleration in the x direction times time. Well, we found out that that's 12. So the initial velocity was 0. The acceleration was 2.5 times 12. So I do the calculation there. 0 plus 2.5 times 12. Notice that this is going to be meters per second because one of those seconds cancels out. And the answer to part B is 30 meters per second. Questions? Okay. That's good, I guess. And so we'll go and we'll look at the next problem, and I'll read the next problem. And Linda, I don't think I'm going to, I think it was useful maybe doing that once, but I'm not going to have the students spend 5 minutes on working on each one as we go forward tonight. Okay, so problem 63, again, it's a similar kind of thing, looking back towards chapter 2. A state trooper is traveling down the interstate at 30 miles per hour. He, in this case, sees a speeder traveling at 50 miles per hour approaching from behind him. Now, by the way, it's usually not a smart thing to pass a state trooper, particularly if you're going too fast. But maybe this person's not paying any attention and they're just, going fast. So they pass a state trooper, and this guy is a speeder. So he's traveling at 50 miles per hour, approaching from behind. Now, at the moment the speeder passes the trooper hits the gas, probably turns their light on to chase after the person, and gives chase at a constant acceleration of 2.5 meters per second squared. Now, they have to accelerate to catch up with the speeder, the criminal, and so they have to be accelerating. Okay, so assume that the speeder continues at 50 miles per second. They're not trying to run away, and they're also not pulling over. They're just totally oblivious to the whole thing. So the speeder continues at 50 meters per second. How long will it take the trooper to catch up to the speeder? And part B is how far down the highway will the trooper travel before catching the speeder? Now, this problem is very similar to the first one, but here we go with this. It's similar, but it's different. They're not starting at a stoplight. Okay, now this was the one we just did. But we go to the very next one, which is this. Okay, now here's some facts. The trooper's initial speed is 30 miles per meters per second, because that's how fast he was going. And his acceleration, once the person passes him, he starts accelerating right away to catch the criminal. And his acceleration is 2.5 meters per second squared. And remember that the speeder's speed is constant. There is no acceleration. They're going 50 meters per second. Okay, from the point, then part A, from the point at which the speeder passes the trooper to the point at which the trooper catches up to the speeder, both will have traveled the same distance. Okay, so that means that, and here I'm going to, underline this again, I guess. Okay, so what we have is that their initial velocity plus 1/2 the acceleration times the time squared is going to be this is the final, this is what the trooper travels. This is the state trooper's velocity times the time. Okay, so the trooper was going at 30 miles per hour, so it's 30 times t plus 1/2. His acceleration was 2.5, and that's going to be, and we want that to be, and that is his velocity times the time. And we multiplied both sides by t. So here we start with this equation. His velocity plus 1/2 the acceleration times the time is going to be his, and so this is his average velocity is the difference between those two. Okay, and we're going to divide by, so we have this, and so we have that t is going to be 2 times v sub s minus his initial velocity divided by the acceleration. Okay. All right, so that's going to be equal to 16 seconds is the answer to this, because that is going to be how long it takes the, and I don't think I'm happy with this. Let's see, how do I get rid of that? I don't really know how to get rid of that. Okay, but what we find out is that the time is 16 seconds. So it takes 16 seconds for the trooper to catch up. But the distance covered by the speeder and the trooper, when the trooper catches the speeder, is it's going to be the velocity of the speeder times the time is 50 miles per hour times 16 seconds is 800 meters. Okay, So you see that the constant velocity of the speeder that's here on the, let me try to get my thing again. So the constant velocity of the speeder, which is on the right-hand side, has to be the same as the constant velocity, the distance, which is rate times time, has to be same as on the other side when we take rate times time plus 1/2 the acceleration times t squared. Okay, so we set those two things equal to each other, and we can cancel the t out. That's what really happened here. Going from here to here, we canceled the t out, and then we solve this for t. So we're going to subtract v0 t from both sides. We're going to divide by a and multiply by 2. And so we get time was this, and it was 16 seconds. And then both of them travel the same distance, so I could put 16 into either of those equations, either the right-hand side or the left-hand side, and I get 800 meters. Questions about this problem?
So I have a question.
Go ahead.
Why are they allowed to cancel a t from both sides of the equation?
I'm assuming Linda is asking the students that. Well, I guess I'm willing to answer it and no one seemed to be jumping up to answer it, Linda. And I sort of answered this on the first problem when I subtracted and factored. And so I could do that again, Linda, or do you want to say something about it? It's up to you.
So since the trooper and the speeder do hit the same position when the speeder passes the trooper, that would be the t equaling 0, similar to the first problem where the automobile passes the truck, but they were at the same position initially. So that's why you get that t equaling 0. That would be another answer here, but it's not the answer that we're looking for, since we're looking for when they actually meet after passing.
And in physics, they don't always, explain all that, but that was a good explanation that Linda provided. Okay, let's move on. And actually, oh wait. Okay, Amber, I don't know if there's any, yeah, there is a lot of math here. I guess that will be my comment to Amber's comment. Yeah, okay, and yes, but no frowny faces allowed, okay. Now we're about ready to talk about vector motion, but before that, I'm going to race ahead because we're going to talk, and I'm going to give Linda an opportunity to talk, and this is called the range equation in 13 microsecond rule. And some of you guys are going to get excited about this because this actually is something that is on ultrasound certification exams and things like that. Now, distance is equal to rate times time, or if I'm talking about it here, it's going to, and Linda, I'm going to let you do this on, I'm going to ask you to maybe use Excel just to do this so people can see how it will work. But we learned that distance is equal to velocity times the time. But now we're going to talk about ultrasound. So here is a person's skin, and this is the thing that we've learned when I gave that little lecture about ultrasound. This is called the transducer. And so you're there. But now you're going to find a thing, and it could be a tumor or something like that, but it's down here. But what we're interested in is how long does it take to go down and hit this object and have the signal reflect back to the transducer. Okay, and for the sake of this discussion, I'm going to suggest for Linda and for everybody else that this thing that you're hitting, the distance from here down to this thing, is 1 centimeter. And 1 centimeter is, well, there are 2.5 centimeters in an inch. So you can see this isn't very deep in the person's body when you're hitting this. And what happens is this is sound. So sound is going down, hitting this, and then going back. And so what happens is we have to be concerned about the velocity of sound in soft tissue. And the sound does travel different speeds depending on what medium you're going through. And so the speed in sound is 1,540 meters per second. Now that's pretty fast. And that is through soft tissue. And that's a number you probably want to remember because it's, that's what we have. But I'm going to ask Linda to speak to this a little bit in Excel. And Linda, if it turns out that, 7's misbehaving or, for some reason you can't do it, just tell me and I can do it. But the students like it when you, talk to them. And so I think this is a good one for you to pick up from this. So that's the velocity for sound in soft tissue. But then this is called, in ultrasound terminology, this is called the range equation, and it's one of the things I'm supposed to be teaching, and I'm teaching it to you now because this is really motion in a line. Okay, so the range equation, and we're going down one, and we're hitting something 1 centimeter, and we're getting it back, and then Linda will probably explain why this is called the 13 microsecond rule. Linda, have I explain this in a way that you're comfortable with, or would you rather not do this tonight?
I think I'm gonna let you do it tonight. I'm just still feeling really sleepy from my COVID booster.
Okay. Something, this is a digression. I got my COVID booster the same day that Linda did. And actually, I went over to talk to Linda, and they said, "Oh, she's gone. We think she went to get her shot." And I thought I should go get my shot too. So I went over and I got my shot. And Linda, it made me sleepy too. That was my main thing. Okay. All right. So distance is equal to, you could say rate times time, but it's velocity times the time. But the velocity of sound in here is 1,540 meters per second. But how far did this thing go? It went down 1 centimeter and it came back 1 centimeter. So this is the total down. In fact, in ultrasound lingo, they would call this the go return time, where going is when the transducer shut it out, and the return time is when it's coming back. Okay, so what we want to do is we want to talk about this. So you got this gadget that's 1 centimeter down here, and what is the go return time for this? So what I'm going to do then is, and I need to think, Linda, were you sharing this, or can I just go to my, I'm trying to think of what I need to do here. Linda, why don't you stop sharing just for a moment? And I will go to mine. Oh, that's not the way this works. This is not, there we go. Okay, so I'm going to start sharing my application screen, and we're going to do, so I'm going to call up Excel, and I'm hunting for Excel here. And yes, Excel is a good thing to use in the physics as well. And here's Excel on my thing. So I will share. I don't know why that wasn't sharing. Here we go. I'm sharing. And now I'm going to throw up Excel. So here is Excel that will be showing soon. And Excel starting to fire up. And again, we're going to use units because units matter. And this, of course, is taking forever, but there it is finally. So we'll go here. And I'll make this bigger so you can see it. And Linda, you can see Excel, yeah?
Yes, I can.
Good, thank you. Okay, so I'm going to write a few things here. Okay. And so this is something that is important for you to remember. Note that the speed of sound in soft tissue is for the most part what you're doing your ultrasound work with is, and this is 1540. This is meters per second. Okay, so this is 1.540 meters per second. Now notice that is meters. And then what I'm going to say is, how long is the go return time for encountering an object 1 centimeter deep? Okay, so now you want to think about this because this is the go return time. So you see the sound went down, but also it came back. And so that was going down was 1 centimeter, and coming back to the transducer was 1 centimeter. So we went 2 centimeters. But this speed is given in meters per second. Okay, so it's 1 centimeter deep, but the distance, okay, so that's not what I wanted to do. Got it. Okay, so the distance, all right, so here we go again. That's 2 centimeters, but I'm going to write this way because I got to consider that to be meters is 2 times 10 to the minus 2 meters. Meters. So that's the distance. And you see, I have to worry about my units being consistent because this was 1540 meters per second, and this is 2 times 10 to the negative 2 meters because there's 100 centimeters in every meter. Okay, so the distance, which is equal to 2, and now I'm going to do this as an exponential, and this is E. Let's see. I'm going to see how it writes that because this is going to be 2. I guess I'm going to just say times and this is going to be 10 to the, and I'm going to put this in parentheses so it's there. And I think that Excel will probably change this into exponential notation. We'll see. So this is going to be minus 2. Okay, so I'm entering that with Excel. And well, I just wrote it that way, but that's fine. That is 2 times 10 to the minus 2. But then I'm going to say that that's equal to 1540. And then this is times t. So if I'm solving this equation, then I'm going to divide both sides by 1540. So I will get that t, again, is equal to, but then the number that I get for t is going to be equal to this 0.02 divided by the 1540. And I get that. Now, this is 1.2987, and this is the exponential e to the minus 5. But if I were to write this as, if I were to move the decimal point one place this way, I would have 1.298 and so on and so forth, which is almost 13. And so this would be, if I move the decimal point, I would have this as 13. And this is called microseconds because it's 13 times 10 to the minus 6 microseconds. You see, if I multiply by 10 over here, I divide by 10 over here, so there's 13 microseconds. So this exercise that we did was applying this to ultrasound phenomenon, but this gives rise to what is the 13 microsecond rule. And the 13 microsecond rule says this. Now we'll talk about this again, but when we talk about it again, we're not going to spend very much time on it. To go and return an ultrasound signal from an object 1 centimeter deep, it takes, and they will say 13 microseconds. So this is the 13 microsecond rule. That is on your certification exams. That will be on the final exam in some respect. Now, I'll probably ask you in the context of a word, but let me just ask you this. So think about this. Suppose that it took 26 microseconds to come back. How deep was the object you hit? Well, the answer is it was 2 centimeters deep because the velocity is equal to, the velocity times the time is equal to the distance. So it's directly proportional. Okay, so anyway, that's the example of this. I'm going to pause for a short time just to see if there's questions about the 13 microsecond rule, but this is really ultrasound kind of stuff. Okay, so that's, and actually someone may have asked a thing. So I think what I need to do is I need to stop sharing this. Maybe I need to stop sharing completely. I'm going to go back to, let's see. Somebody was making a comment. I guess I have to stop sharing. Oh, I can stop sharing.
If you click on the little chat icon next to my name on the bottom, then that'll bring up the chat.
Okay, the chat icon down. The chat icon next to what?
So right where it shows my name on the bottom right-hand corner, then next to that on the white menu, then there's a little chat bubble with a 1 next to it. You should be able to click on that.
Oh, okay, I clicked on that, good. So this is something we should be using on the job, yes. And in fact, you're going to be using this before you're on the job because you want to pass the certification exam before, in fact, you will pass the certification exam before somebody gives you a job. But yeah, you could use it on the job because if somebody says, how long does it take? Any ultrasound person worth their salt will know that it is what the 13 microsecond rule means, okay? All right, so that's good. Let's move on. I was just trying to do a little ultrasound things. But now I'm going into 2 dimensions, and we're going to do at least one problem here. And again, I made a whole bunch of videos with a number of examples. Now, in projectile motion, there are 2 things happening. And in fact, there's a nice little picture of a projectile motion down here. And what's really happening is something's going up and something's going down, but you're shooting it at an angle. So it's like you throw a ball, it goes up and then it comes down. And that's the picture that I drew that little figure next to. So that's what's happening. But this is more complicated because we have motion in the X direction and we have motion in the Y direction. And we combine these because this goes at an angle, we're going to be using the vectors. So you see in this case, this vector for the initial velocity was going this way. So that's at an angle. And so you have the upward direction and the horizontal direction. So there's the up and down, the horizontal, and those are independent of each other. But what I'm going to tell you is both of those, both the X and the Y, use the equations that we just talked about in chapter 2. But they're independent of each other. The Y is independent of the X direction. And I show you a nice strobe photograph in the videos. And even if you haven't watched the videos yet, please go watch the videos because I think they're good. But now we're going to use these kind of things. But remember what I said, and just trying to emphasize it, that the X direction is independent of the Y direction. And so we're going to be using vectors to do this, but we're going to be considering X and Y independent. But both X trajectory and the Y trajectory are being governed by the same rectilinear equations from chapter 2. So the thing I put a little mark by there, those are really the same equations that we saw before. Okay, now we're just going to dive in and do a problem. Okay, so I'm going to read this problem and we're going to work it because I am being jealous of our time. And so we're going to work this, this problem. A physics book slides off a horizontal tabletop with a speed of 1.10 meters per second. It strikes the floor in 0.350 seconds. And if we were in the classroom, I actually would take a physics book and I would put it on the table and I would shove it along the tabletop at a certain speed and you'd see it fly off and you'd see it hit the ground. We can't do that here, but that's kind of okay. And we're ignoring air resistance. We want to find the height of the tabletop above the floor. We want to find the horizontal distance from the edge of the table to the point where the book strikes the floor. And we want to find the horizontal and vertical components of the book's velocity and the magnitude and direction of velocity just before the book reaches the floor. Now I'm going to sketch a little bit of this here for you. Again, I'm going to draw a little bit of a picture. So here is the tabletop. And again, forgive this isn't a great picture. But anyway, here's the book. And most physics books are big, so that's a big book. And we're shoving it along. But you see, this only has horizontal velocity, and the velocity that it has is 1.1. There's another 0 there, meters per second. So it goes over here. Okay, so it is going 1.1 meters per second, and we are ignoring air resistance. We're also ignoring the friction of the book on the table. Okay, so what happens is you shove it over here, and this is what will happen with the book. It will start dropping, and it will hit the ground. But you see it went a certain distance down here, which is how tall the table is, but it also went this distance in the horizontal direction. So you see there's some things going on here. So I'm going to remind you of a few things that are happening. So in the x direction, the initial velocity is, that's in the x direction, is 1.1 meters per second. So that's what's happening. When it gets away from the table, what happens is the initial velocity in the y direction is 0 at that instant, but there is an acceleration, and the acceleration is given by g, which is the acceleration due to gravity, and g is 9.8 meters per second squared. Again, that's another number that you want to remember because it's going to be involved in many problems. And remember that the x and y directions are independent of each other. So now I'm going to solve this problem. So I'm going to the next page, and we will talk about this. Okay. Now we're going to take, and you are free to do whatever you want, but we're going to take y to be the downward direction. I think I need my pencil again. So y is downward. Now the acceleration in the x direction is 0, but the acceleration in the y direction is, you can see that is what I call g, which is 9.80 meters per second squared. The initial velocity in the x direction was 1.10 meters per second, and the initial velocity in the y direction, and this was the instant when the book ran out of table to be pressed down on, the initial velocity in y was 0.2 because we were just letting it fall. We weren't throwing the book down. Okay. So now we're going to look at those equations that we have. This is the equation, and notice that this is the equation in the y direction. So y minus y0, and by the way, y minus y0 is going to eventually be the height of the table, okay? Because that's how far did you go, and that's equal to the initial velocity in the y direction times time plus, this is 1/2 the acceleration in the y direction times the time squared. Now that's one of those fundamental equations we're going to be using over and over again. But all the students should realize is that we don't know y minus y0. That's what we want to find. So we want to find y minus y0, but we know everything on the other side. V0y is 0 from our discussion before. And then I have 1/2 the acceleration in the y direction is 9.80 meters per second squared. And then the time squared, we already told you, it took 0.350 seconds to hit the ground. So you see, I can plug those numbers in to the right-hand side of that equation and see what I get. And when you do the arithmetic, what you get is this is 0.600 meters. Linda, we started recording this, didn't we?
Yes, we did.
Good. Okay, so I'll post this later tonight, maybe during my office hours. So this is the height of the table. So the answer to this part of the problem is that. Now, you had to figure that out first, because, and not just because it was part A, you had to figure that out first anyway, because you needed to know how long is the book going at this 1.1 meters per second in the X direction. Well, that's what part B was about. So we're saying, okay, and notice it's the same problem, except we have velocities that are in the X direction and accelerations that are in the X direction instead of in the Y direction. And so we're using the same equation. So we're saying the change in distance is the initial velocity times t plus 1/2 the acceleration times the time. Now, there was no acceleration because the book just always was moving at 1.1. There was no acceleration, there was no deceleration. So AX, and we already talked about that, was equal to 0. So this is just going to be 1.10 meters per second times 0.35, and you multiply those things together and you get 0.385 meters. So that tells you how far you went horizontally before you hit the floor. And this also told you how long it took to hit the floor. I mean, we already knew that, but how tall the table was. So we have that. Now, the last question that they ask is, how fast was it going? What was the velocity when it hit the ground? Now this requires you to realize that, and I'm going to draw a little picture here down, it didn't hit the ground straight, it hit the ground at an angle. So you see it was going down. I don't like the way I drew that. So I'm erasing that. You see, when it hits the ground, it's going at an angle because it's moving down and it's moving to the right. So I'm going to try to draw that again. So you see it's moving to the right and it's also moving down. That means this is a vector. And so we want to know what is the magnitude of this vector. So the x component of this vector was 1.10 meters per second. Here is the x component of the vector. So this was the 1.1 meters per second. Now the y, it was going down in this case, and so the y velocity was this equation. It's the initial velocity, which we know to be 0, but the acceleration is 9.8 times 9.80 times the time. So that is 3.43 meters per second. So this is 3.43 meters per second. Both of these are meters per second. So I can use the Pythagorean theorem to find out what this v is. What is the velocity at the instant this hits the ground? Well, it's going to be, this is the Pythagorean theorem. So I'm going to square the x number, which is 1.1 squared, plus I'm going to add the square of the y number, which is 0.343 squared, and then I'm going to take the square root of it, and I will get 3.6 meters per second squared. Now that is the magnitude of this, but it's magnitude and direction. So we need to know what is the angle, and the angle is going to be that it's hitting the ground is at 72 degrees. Now the way you found that out was, and this is a review of what we studied in the vectors, and yes, you see you do have to use that. That's going to be that the tangent of this angle, you might say, where is this angle theta down here? This angle theta is right here. That's what angle you're hitting the ground at, is going to be 3.43 divided by 1.1. That's the tangent of theta. You're going to do the inverse tangent, and you're going to find that theta is equal to 72.2 degrees. So the velocity of the book just before it hits the floor has a magnitude of 3.60 times 3.60 meters per second, and is directed at 72.2 below the horizontal. And below the horizontal means that this angle here is also theta, because that's below the horizontal, but those are the same angles because of geometry that you studied when you studied geometry. Those two angles are the same, because in the theorem you studied in geometry was parallel lines cut by a transversal, the alternate interior angles are the same. Now I want to pause because this is probably the most involved problem that we've done so far, because we had independent things happening in the X and Y directions. So that was new. We had all our vector business happening, and we had all these rectilinear motion equation things happening. So this was a reasonably complicated problem. If I was just messing around in class, I'd say, Linda, how much harder was this problem? But I'd say this problem might be 3 times as hard as the other one. At least there were 3 more things that were involved in doing this. So I'm going to pause for a count and find out if people want to ask questions about this one. Okay, now Linda, I hit 10 Mississippis and there were no questions. Do you think that means everybody understood it, or do you think that maybe that means some people might want to be going to the GSGs or something?
I think people should definitely be headed to the GSGs in some office hours. Someone in the chat is already saying that they're having trouble understanding, so this is something that you guys definitely want to take advantage of.
Okay, and again, sometimes students will say, gee, I don't even know how to ask a question here. Well, you just take it one line at a time, okay? And bite off a little. In fact, there's a joke people sometimes say is, how do you eat an elephant? And the little joke is, you eat an elephant one bite at a time. Well, that's the way you solve this problem, one step at a time. But this is I think this is a significant step for you, and this is different. So going to the GSGs would be a good thing, and all of that. Now I think I'm going to go, and we might not have time to do another problem in this much detail, but we're going to talk about some other problems, and that's fine. And sometimes students say, hey, I'd like to have more problems to work on anyway. Well, I'm giving you more problems to work on here. So let's go to the next slide. Here's a different problem. I'm just going to read it. But I think you'll see, oh, it's related, but it's a little bit different. A military helicopter on a training mission is flying horizontally at a speed of 60 meters per second, much faster than you can shove a book across a desktop, when it accidentally drops a bomb, fortunately not armed, at an elevation of 300 meters. That's pretty high, and you could ignore air resistance. How much time is required for the bomb to reach the Earth? That's a similar question as to one we did before. How far does it travel horizontally while falling? Find the horizontal and vertical components of the bomb's velocity just before it strikes the Earth. I think there's a lot of similarities here. and you don't have to draw the graphs, I suppose, but if the velocity of the helicopter remains constant, where's the helicopter when the bomb hits the ground? And so those are some good questions and some things that you could practice on. Let's look at, oh, that's I guess that's a solution. Here's some others. A daring swimmer dives off a cliff with a running horizontal leap. So they dive off, but they don't want to hit the ledge, they want to hit the water. So the question that's being asked here is, what's the minimum speed they can be running with their leap so that they clear the ledge, because they would hurt themselves if they hit the ledge. And again, I guess there's solutions here, but you have to understand the solutions. This talks about some champion insects jumping and grasshoppers jumping. Here's something jumping off a wall, and you're trying to figure out how high it went, or something. There's a whole bunch of questions here. In fact, there's two questions here, 21 and 22. But now the thing I really want to get to, because I'm almost to the end of this, is this one, which is the LSA called Physics 3. So I am going to read this, and this is something that you want to get done. And you have Physics P0, you have P1, P2, and now P3. Now I think I put 0, 1, and 2 all being due at the same time in the announcements in the email I sent. This one I'll make due a little bit later, but still you want to be thinking about it. So a test rocket is launched by accelerating it along a 200-meter incline at 1.5 meters per second squared, starting at a rest point A. So you're accelerating this on this ramp. The incline rises at 35 degrees here above the horizontal, and at the instant the rocket leaves the ramp, its engines turn off and is subject only to gravity, and we're ignoring air resistance. Find the maximum height above the ground that the rocket reaches, and realize that the rocket goes up and then it goes down, and the greatest horizontal range the rocket beyond point A. So from point A, how far did it go before it lands? And I am going to draw again kind of what's happening. So you see it goes up like that, so it goes up, and actually it probably goes up more than that, but then it comes down and it hits the ground. So you're finding how high does it go up and how far does it go over. So these are fundamental questions, and I'm sure that I'm going to be asking vector questions, and I'm going to be asking questions that are similar to these LSAs on the physics final exam. So you want to engage and make sure you're understanding this stuff. Okay, I'm going to go ahead one more slide and just see what I have. This has to do with somebody hitting a home run. And so there's a batter, they hit a home run, and the home run goes a certain height. I guess I lost my thing again. Since we were talking about LSAs, that's right. Just upload the PDF no answer sheet this time. And thank you, Amber, for bringing that up. But that's the answer to that. Okay, and I'll start, and I think there are LSA places for P0, P1, and P2. Okay, Linda, I think we've reached the end of this, so I'm going to turn the recording off and tell the students that they can come to my office hours at 9 p.m. If they want to, and and certainly Linda's GSGs happen right before class. Linda, is that right?
Yes, it is 5 to 6 on Mondays and Wednesdays.
Okay, excellent. So that would be a great thing for you to do, and Linda will be, I'm sure, completely recovered from the the shot by that time. Okay, so we are good to go. I'm signing off right now. You guys take care of each other. Do the math; it will make you strong. So I'm going to turn off the recording.